common CNN architecture. Okay, so let's start with the introduction. So to understand the convolutional neural network, I would like to start with the convolution function. So by definition, the convolution is a mathematical operation on two functions, for example, f and g, and the convolution will produce a third function. This is the annotation for the convolution, right? F star and g. And this function will express how the shape of one function, f or g, is modified by the other, right? So actually we can see that the f star g will be equal to z star f, okay? So it will produce the integral of the product of the two functions after one is reversed and shifted, okay? So in this formula, we are seeing that, okay, the convolution is like we have the integral from negative infinity to positive infinity, right? And here we shift the z function by an amount of t, and this is I mean the negative here is referred to the reverse, right? Okay, and again it is the same as we shift and reverse the f function, right? So this is an animation for the integral of the product of f and g. So you see this is a result when we convolute the two functions with the shape in blue and red, right? And we get the triangle shape, right? Okay. So a convolutional network is a neural network that uses multiple convolutional layers, right? So it will use multiple convolutional layers, and this type layer will exploit the spatial structure characteristic of the data, right? And the idea is to use multiple identical copy of the same neural network, right? And by this way, we can have a network that have a very big number of neurons, very big number of parameters, right? And we can also have a network that have a very big number of layers, so that we have a deep network, right? But because we use multiple identical copy of the same neuron block, so that the number of weight that need to be learned for the model is significantly smaller. So that is the idea of convolutional layer. Okay, let me correct the slide a little bit to remove the Vietnamese version. Okay, so take a look in this figure. We can see here is a CNN working on two-dimensional data. Okay, in the bottom layer, we have the input. It is actually a two-dimensional matrix, right? Okay, so the size of the matrix is 9. Right, and 1, 2, 3, 4, 6, 9 matrix, right? Okay, and what we have is here is this is a intermediate, the hidden layer. It is a hidden layer, and it is a fully collected layer as the output layer, right? And we can see that for the hidden layer, it is actually a convolutional layer, and you are seeing that we have the multiple blocks which are the same, A, and here B, right? They are the same block, right? And that was the idea of the CNN, using multiple identical copy of the same neuron block, right, for the layer. So you can understand that for this layer, okay, we have many neurons, but the actual number of weight to be learned is very small, because what we have to do is only to learn the weight inside the block, okay, and the block has the input from four, label the input, right? And this is the same for the second hidden layer. For this layer, we can have the entire layer, but the number of weight to be learned is only the weight inside the B block, right? And that block is replicated all over the layer, right? And of course, we can apply many convolution layers this way, okay? And then in the final layer, this is a fully connected layer, will be used to produce the, for example, the classification prediction, for example, right? Okay, so the neuron block in the CNN can be a small neuron network, right? And they are called filter or kernel, right? So for example, this can be an implementation of the block, right? And for the image processing, people have been using the convolution for a long time ago, and you can see here is an example of using the kernel for blurring the image, right? This is input image, right? And this is output image. So you see that in that output image, the quality of the image is blurred, right? Right? How? By applying the kernel. This is a 3x3 kernel, right? And you see the weight in the kernel. So actually, if you refer to the way we have the convolution layer in here, you might see that okay, the idea of the weight in the kernel is to how to say multiply with the input, and then this is the weight to weight the different input and produce the output in the output image, right? And here you might see that okay, every neighborhood in the input image, right, will be multiplied with the kernel, and then we produce the output is like the weighted average of the input, right? And that's why we can produce the blur image, right? And also we can use the kernel here to extract the the contour of the image, right? Depend on the filter that we can visit different output that produce for different objective. Okay. Okay, this is the illustration for the work of the filter. We have the input image of size 5 multiplied by 5, and we have the filter 3x3, right? So the idea of the filter is to slide over the input from left to right, and also from top to bottom, right? And on the way we slide the filter, we multiply the filter with the input, with the corresponding input, and then it will produce the output, right? Let me pause how to say, let me stop the image, the animation. Okay, now it's stopped. Okay, so I don't know how to stop it, but oh. Okay, so take a look into this. So this is a computation for the last top right piece of the output, right? And you see that this is a filter over the input, and you can multiply the input with the corresponding element in the filter, and then it will produce the result. Here is number 4. Okay, 1 1 1 and 1 here is 4. The other is 0 because you multiply the input with 0. Okay. Okay, so now we move to the second part about studying a little bit about the history of CNN. So the CNN first came from the work of Fukushima in 1980. Right, it's a paper of the neocognition. Okay, and then in 1998, Jan LeCun applied backpropagation to train the CNN for the text recognition problem, right? And it's the paper named Gradient-Based Learning Applied to Document Recognition. The idea about this paper is to train a neural network that can classify the writing character, right? Okay, and by 2012, the CNN made a big splash when they won the ILS RC 2012 competition, and actually the performance was far surpassing the second method of the traditional computer vision approach. By saying the traditional computer vision approach, I'm saying about the approach that follow the test, the way so that you have to do manual feature engineering and then apply some kind of machine learning classification to predict the image label, right? And by using a CNN, you can automate the process in an end-to-end fashion. You fact the image as the input of the neuron, and then you have the label as the output, and then you train the neural network for this, right? Okay, so yes, but about this, you should understand that the success of CNN, right, start with the big, number of training sample. It's a ImageNet dataset. It was the biggest image classification dataset was released at that moment, right? Before that, there's no big dataset like ImageNet, and maybe that was also the reason that it is not necessary. It is not easy to train a neural network with small dataset, right? And then you see the application of CNN almost everywhere. For example, in image classification problem, and also for image querying problem, right? Okay, on the left, you see the classification result. Okay, this is the input image, and this is the prediction. Actually, you get the probability of the class, right, for an image. And here is say it have the highest probability for the container zip, right? Okay, it's the correct. Highest probability for the motor scooter, okay? Highest probability for the leopard, right? In some cases wrong, is the here is the green, but it's predict conservative, right? This mushroom is predict agaric, and cherry predict Dalmatian. Okay. And also for image querying, right? CNN was used to learn the image embedding, right? The vector representation of the image, and then you can use that image to query for similar image in the database. For example, yeah, you put an image as a query, and then the system can return to you a list of similar images, right? List the image about the image of flower, image about the elephant, about the sheep, about the pumpkin, and about the dog. Okay. This was also used for object detection in the image, right? So here you see the faster RCNN implementation in 2015, and it can predict the class for the object in the image. Okay, it's predict here is a person, here is a horse, here's the person, here's the dog, and here's the car, right? And this is bus, right? This is person inside the bus, right? And the CNN also used in semantic segmentation, right? So instead of predicting the bounding box for the object, it can actually, predict the segment for each object in the image. For example, it predict here it is a boundary, and it's correct coloring the human, for example, right? And it is the tree, okay, and correct boundary for the tree, and it is the correct segmentation for the road, right? Okay. Okay. So you also see the CNN for almost every model for the image. Here we use the CNN for pose prediction, right? And actually now you can predict the pose of the person on the image in real time, and the model can also deploy on mobile and embedded environment, right? So thinking about the mobile application that incorporates the model, then you see that it can have a very nice application, a very nice game, right? And also it was used for game play, right? So there's a model that can detect and extract the object in the screen, and then that information was used to train a model that can play the game automatically, right? I remember in the past few years ago, someone write an application that can play Flappy Bird automatically, right? Okay. Any questions so far? Do I have any question? Okay, if not, then we can move to the next part of the lesson. Here we discuss about different type of CNN layer. Okay, so first, the convolutional layer, right? And usually write conv as an abbreviation. And unlike a phony collected neuron, a convolutional neuron, or you have another name, filter, is only locally connected to the input, right? Okay, it is a filter, right? And at this moment, at this point in time, it is only locally connected to the input data, right? At this, region. The convolutional neuron slide from the left to right and from top to bottom, right, at the input block, and compute to generate an activation map. So the output after the convolution is called an activation map. This is just the name, right? The depth of the convolution neuron is equal to the depth of the input data block, right? In the example we have here, the input is 3-channel image. Let's say it's a RBZ JPEG, right? And the size of the image is 3032, and we have 3-channel red, green, and blue, right? And what is said in here? It is said that the depth of the filter equal to the depth of the input data block. So actually for this filter, the depth of the filter is also 3, right? And the size is 5 by 5. The image is 30 by 32 by 32 and by 3 image. Okay, and the output is named an activation map, and the size and the depth is 1. Okay. So this is an illustration for the convolution layer slide over the input. You see the direction of the slide is from left to right and from top to bottom. Okay. And you have some parameter for the slide, such as the strides. Here you have the stride equal to 1. You move 1 block, right, from left to right and from top to bottom, right? If you have stride equal to 2, actually you will move from here to here, right, and from here to here. Okay. The input size 7 by 7, the neuron size 3 by 3. Then in this way, the output will have size of 5 by 5. Okay, any question? This is understandable, right? Okay, I don't see the comment often, so if you have any question, please talk, okay? Okay, I should remove this slide. Okay, so you have the formula to calculate the output size after the convolution. The size of the input is n minus f, and then you divide by stride, and then you plus 1. For example, this is the size of the input, it is the size of the filter, and in the case you have the stride equal to 1, then the output will have size 5. If the stride is 2, then the output is 3. And if the stride 3 and the output is a float number, and this is something that you want to avoid, right? Okay, so you see that in most of the case, the size of the output is smaller than the size of the input, right? And if you want to preserve the output size to be similar as the input size, you will add the padding border. Usually you add 0, and this called 0 padding. And for example, here is an example of padding with 0 over the border, right? And if you pass the data this way, then the output will be having the same size as the input. For example, here the input size is 7 by 7, the neuron size is 3 by 3, stride 1 with no padding, then the output size is 5, right? And now you padding with 1. You padding with the size of 1, then the output size is 7 by 7. It's the same as the input, right? Okay, so remember that for each convolution neuron, right, you have one activation map, right, as the output. And assuming that another convolution neuron is added, then it will behave similarly and it will generate a second activation map, right? And in this case, you can produce another image, right, with this sign and then the number of the channel, right? Note that the weight of the convolutional neuron are different, right? Because you want a convolutional neuron to learn different things, right? Okay. So assume that in this example you have a 6 convolutional neuron, then they will generate a 6 activation map. And I mean, when you stack the activation map together, and it form a new image, right? Actually, in this image, it have a 6 channel, right? I mean, I'm not talking about the RGB image, but actually here you can name it a new image, right? Okay, with the size and number of channel. Okay. Okay. So CNN, a convolutional neural network, is a sequence of convolutional layer stacked on top of each other, and they are interspersed with activation function, for example, value or time or sigmoid, whatever, right? Here is an example. You have the input image with the size 32, 32, and 3 channel. First, okay, you fed to the convolution layer and then the activation, right? And then this is the output image, output activation map. And then you fed to another convolution layer and the value, and then you get all the image, right? And then of course you can stack many convolution layer and activation function to make a deeper CNN. Okay. Okay. So this was about the convolution layer. Now we will discuss about the pooling layer.
Teacher, can I have a question? I see that the channel is different from the depth, right?
Sorry, what was the question?
I wonder if the channel is different from the depth. I mean, for example, 6 channel and 3 depth here.
Actually, it means the same thing, right? Here you can say that, okay, the initial input have a 3 channel, or the deep dimension is 3, and here you can understand that, okay, the image is 28 by 28 and the deep is 6, and you can also say that, okay, it have 6 channel, so it means the same thing. I'm not talking about the deep of the network, right?
Yeah. Okay.
Okay. So now we discuss the pooling layer. So pooling is actually a downsampling technique, and it has to reduce the block data resolution in order to reduce the memory and the computational consumption, right? And this is an example of the pooling layer, right? So in this image, in this example, this is a initial image with size 224 by 224, and by downsampling, I mean that I reduce the size of the image. For example, in this case, I reduce the size to be a half, 112 and 112, right? And the pooling mechanism is the same mechanism for the activation map. Right? For example, here is a input image, or you say it is an input image activation map, right? And in this one, you see the size of the input is 224 by 224, right? And by pulling, you get a new activation map that has the size only by a half, right? 112 and 112, right? And in this case, the number of the layer remain the same. For the number of activation map to remain the same, 64, 64, right? So the pooling layer work independently on each activation map. You have one specific implementation of the pooling layer. It's named mark pooling layer, right? And the mark pooling layer have the network to make the representation become invariant to the small or local translation or information of the input data. Let me give you the example of a mark pooling layer. So assume that we have a single diff slide image, right? And it has the size 4 by 4. And now we do the mark pooling with 2 by 2 filter and strike equal to 2. And then this is the output, right? So in this case, the output has the size of 2 by 2, right? It's a half of the input, right? And you see each element to the of the output is corresponding to the max element. Of the corresponding input, right? For example, for this output, the input is this 4 cell, and for that output, the corresponding input is this 4 cell, and the mark of code is 6 and 8, and again for this output, and again for this output, right? So it will reduce the size and keep the mark number, right? And in that way, we're seeing that the network can make the representation to be invariant to the small translation. For example, if the mark, the 6 is not here, but the 6 is here, then okay, after the mark pooling, we got the same output, right? If the 8 is not here, but it's somewhere here, you see there's some kind of, translation in the image of the object in the image, then the mark pooling can, make it to be the same as the output, right? Okay, you might have the average pooling layer. Actually, you average the input and you write the number in here, right? And average the output and write the number in here. Okay, so this is a typical architecture of the CNN in reality. You have the input image, you have the convolution layer, and then you have the activation function, the value, and then the convolution layer, and then the value, and then you have the pooling. And naturally, you want to reduce the size of the activation map, right? For example, in order to predict the image to be a car, right? You don't need to look into the detail of every pixel in the image, right? You can decide it to be a small size, and you look at the shape of the object, right? Because in this case, if I reduce the size of the image by 4, I still can distinguish the car according to its structure. The geographic structure, right? Okay. After this first pooling, I make another conclusion, and then value, and then conclusion value. Okay, and here I decided to have a new pooling to reduce the size of the activation map. Okay, and again, the dip can be vary, depend on the data and depend on the objective, right? And then the pooling layer here, and then finally, if we want to predict the classification for the input, we can have the fully connected layer with the number output equal to the number of the classes, right? If I had to predict 1,000 classes, then I have the FC layer with 1,000 output, right? Any questions so far in this moment? Okay, one thing I want to tell you is about the learning of the convolution neural network. So actually, for the convolution layer, right, this is a number of parameter to be learned, right? It has a size of 5 by 5 by 3, right? And it is actually the weight of the convolution neuron is the thing to be learned by training, right? And this is the case for convolution neuron. In the case of pooling layer, so by pooling layer, you don't have to learn the weight of the pooling layer, right? Because here is just the mark function, right? Nothing to be learned, right? I just extract the mark from the local input and I have the output, right? So if you have the mark pooling layer, that layer have no learning parameter. But if you have the convolution layer, then the size of the convolution neuron is the number of the parameter to be learned. Is it?
Sorry.
Yes.
I have a question. In the previous slide, you told us the depth of the convolution neuron is equal to the depth of the input data block. So I think that there are two parameters to learn because the third parameter 3 here is equal to the input data block, the depth of the deep input data block. Yeah?
No, actually, what you define is just the set of the filter, and you have no. I mean, you just know that okay, you have this number of parameter to be learned, right? So the shape is a 5 by 5 and 3, right? Let me write a little bit. So this is the filter, okay? You have to learn the value of this matrix, 5 by 5 by 3. Is this understandable?
Okay. Anyway.
Okay.
Yeah.
You just know the shape of the matrix, but you don't know the weight. I mean the cell, the element inside the matrix, right?
Yeah.
Okay. Any questions so far? Any question? Okay, if we have no question, then I might suggest that we take a break of, let's say, 10 minutes, for example, and then we continue. Okay. Okay, so let's continue. So I have one question from Nguyễn Huy Hoàng. How can we choose an appropriate try? So actually this will be something by experience, right? Any other question? Okay, so we can continue by discussing common CNN architecture. We will address the NerNet, Phi, AlexNet, VZZ, Google NerNet, and ResNet in this discussion. Okay, so first about the NerNet. It was actually the network proposed by Jan LeCun at 1998 for the classification of handwriting number, right? And the input is image of size 32 by 32 and one channel because it's a gray image, right? And the network is designed to have the first convolution layer with size 5 by 5 and size equal to 1, right? And in this case, you have the output size 28 by 28, and you have a 6 convolution neuron, so you have a 6 output channel, and then you do the average pruning, right, with the number of filter is 2 and the tries were 2, right, and you got this is the output with size 14 14 and 6, right, and then the convolution layer reduce the size to be 10 by 10, and you have a 16 convolution neuron like this, so it will output us 16 layer, right? And then again for the average pruning. Okay, and then finally you have these final output activation map of the convolution network, right? With the size of 5 by 5 by 16, and then you have two fully connected layer as to make the classification. Okay, the first layer have 120 20 neuron, and then 84, and then at the end you have the output have 10 output like have 10 output, sorry, the output have 10 how to say 10 10 component, right, to be similar to the number of the class, right? Okay, so it was quite a small CNN architecture, but it can predict pretty well the number within a limit, right? In 2012, you have a CNN network that won the IMIDNet challenge, right? And it's what introduced in the paper IMIDNet classification with deep convolution neural network. This was one of the largest CNN network at that time, and that network have 60 million parameter right? In internet, you have only 60,000 parameters. This was huge, I mean, increment over the number of parameters, right? That CNN was the champion of the ILSV RC challenge, Immediate Large Scale Visual Recognition winner, right? And that challenge, I mean, people consider that challenge is as the annual Olympic in the field of computer science, and the team around the world compete against each other to see who had the best model for the problem like image classification and positioning and object detection in image. And for the data sets, usually we have the number of the classes is 1,000. It's big, right? Okay, so before 2012, I mean, the champion was shallow network or traditional classification algorithm, right? And it have a very high error rate. And now, when we apply the CNN with the edge layer, and it reduces the error rate to be less than 17%, right? And then again in 2013, 14, and 15. Okay. This is architecture of the AlexNet. Okay, so the input is an image of 227 by 227, and it is actually a 3-channel JPEG, red, green, and blue, right? Okay, so for AlexNet, the input is fed into the first convolution layer with the size of 11 by 11, stride equal to 4, and the padding equal to 0. And so that the output is 55 by 55, and you have 96 channel, right? And then you fed into one mark pooling layer, right, with size 3 by 3 and stride equal to 2, and then what this is the final output after the mark pooling. And then the convolution layer, stride equal to 1 and padding equal to 0, and you increase the depth of the activation map to be 286, sorry, 256, and then again, right? So you see in this architecture, we use in the first layer is quite big convolution neuron, 11 by 11. And then at the end, we have two fully connected layers with a size of 496 and 496. And then we have the SOMAC layer that have the probability that give us the possibility to predict 1,000 classes. Okay. Okay, so in 2013, in that chance, we have the ZFNet. So ZFNet is just an improved hyperparameter over AlexNet, and we reduce the error rate to I mean 11.7. Okay. And then in 2014, we have BCG and Google NeurNet, right? And for Google NeurNet, we have up to 22 layers. And for ResNet in 2015 is a very big network of 152 layers. Okay, so you see here like the explosion over the network diff. Okay, so now we will continue with the introduction to VZZ and Google Neural Net. VZZNet. So the VZZ is introduced in the paper Very Deep Convolutional Network for Large-Scale Image Recognition by Karan Simonian and Anvil Wisserman in 2015. So it is a runner-up of the SVRC competition in 2014. So actually the winner is Google Neural Net and the VZZ is running runner-up. Okay, so it is much deeper than AlecNet. So AlecNet have 8 layers and the VZZ have a double 19 layer. Okay, the number of parameter is 140 million parameter, right? For the AlecNet, we have just 60 million parameter. Okay. Okay, so this is the architecture for the VZZ net. You have the input and then 2 convolution layer and then the pooling layer to reduce the size by half, right? And then 2 convolution layer and then the pooling and then 2 convolution and then pooling and then 3 convolution and then pooling and then 3 convolution and then pooling, and then you have 3 pooling collected layer with the final to be 1000 size. I mean, that is for the 1000 classes classification, right? So you see in the VZZ net, we have very small filter size, only convolution 3 by 3. We don't use 5 by 5 or 11 by 11, right? As in AlecNet, now we use very small filter, right? Stride 1 and padding 1, and we have a 2 by 2 map pooling stride 2. We have deeper network from 8 to 16, 19 layer, right? And ZFnet is that an improvement of VZZ, right? And you see in the VZZ net, we somehow double the number of layer after it pooling, right? So here you see that we have a, small activation map with, but the activation map is very deep, right? Okay, so the idea about using a small filter, here's an example, right? We have the filter 3 by 3, a stack of 3 by 3 convolution layer, stride by 1, had the same output representation capacity as a 7 by 7 convolution layer, because the output size is the same, right? You have the input and then 7 by 7 convolution layer, you got the output, right? You have the input and then 3 small filter like this one, and the output still have the same size, right? But the difference is we have a deeper, right, more layer, and mean that we have the possibility to learn more nonlinear function, right? And we have less number of parameter, right? And the number of parameter is 3 multiplied by 3 square c square, and in the former case we have 7 square c square, where c is the number of channel of each layer. If c is 3, then okay, you can calculate, and you see that the less number of the parameter we have in the case where we have small filter. Okay, so here we have the illustration for the size of the memory and the number of parameters to be learned in the case of BGP network. Okay, so for the input, the size is 224 by 224 by 3. It needed actually 150k kilobyte, right? And the number of param to be learned is 0, right? And then we have the convolution layer here, and actually the size of the memory to keep that convolution layer is 224 by 224 by 64, right? And it's 3.2 million, 3.2 megabyte, right? And this is the number of param, 3 by 3 by 3 by 60, right? And then this is more than 1000 here. So this is the size to store the output, right, of that convolution. And then we have another convolution, and then okay, the memory is like this, and the param is like this. Okay, and then we have the pooling. Okay, we reduce the size of the output, right? And the param for that pooling layer is 0. I told you before that for the pooling layer, there's no parameter to be learned, right? And then you go down, and then okay, in this pooling layer, you reduce the size of the memory to hold the output is that 400 kilobyte, and in this case, it is 0 param to learn. And then okay, and then for the fully connected layer, okay, and if you do the total summarization over this, you see the size of the network, right? And then the number of parameters to be learned, right? And actually the size of the network here, it will be related to the size of the, for example, the main memory you have, the size of the memory in the CPU card, right? And remember that you should multiply by the batch time, right? Okay. Okay. Any questions so far? Do I have any question? Okay, so let's continue by Google Net. Okay, Google Net. So Google Net is proposed in the paper Going Deeper with Convolution at in 2015. It is a winner of ILSP 2014. Much deeper than AlecNet, but it have a travel time fewer parameters than AlecNet. And the Google Net focus on reducing the computational complexity, right? Now we will discuss how we can design the Google Net that have fewer parameters than AlecNet, but it's also deeper. Okay. So this is the architecture of the Google Net. Right, it have 22 layer. So for the Google Net, they use a special layer that needs a inception block, and this is a inception block, and this is an inception block. Right, we will discuss this block in detail in the next slide. And for Google Net, they have no fully connected layer, right? Only 5 million parameter. Okay. Now we discuss the inception block, right? So for Google Net, the naive inception model is the following. an inception model consists of one by one convolution and 128 channel, right? And one 3 by 3, 192 channel, one 5 by 5 convolution neuron with 96 channel, and one 3 by 3 Marconi, right? And for example, this is the inception that work in the with the input of the previous layer with size of 28 by 28 by 256 channel, right? And then the output of the convolution layer will be concatenation. Okay, and now let's discuss the number of computation. For the first 1 by 1 convolution 128 channel, this is the number of computation, right? 28 by 28 by 128 and by 1, and this is the input channel, right? Okay, and the same for the second block, and the same for the third block, and then the total operation for this inception model is 854 million operation. So it is actually heavy load, right? A lot of computation in this naive inception model. GoogleNet proposed to use a bottleneck convolution 1 by 1 to reduce the block diff, right? So okay, before that 3 by 3 convolution, the GoogleNet proposed to use 1 by 1 convolution, and so 1 by 1 convolution before the 5 by 5 convolution, and after the Marconi you have 1 by 1 convolution. Now we calculate the number of computation. Okay, so 1 by 1 convolution 64 channel, this is the number of computation. 1 by 1 convolution 64 channel, okay, it's the same number of computation, right? And now we have a 1 by 1 convolution 128. Okay, this is number of computation. 3 by 3 convolution, okay, this case, okay, so in this case this is only 28 by 28 by 192 by 3 by 3 by 64, right? Because this accept the input which was the output after that 1 by 1 convolution 64. Okay, and the same for this convolution, and the same for this one. And now you see that we have a very big reduction in terms of number of computation. And here for this inception block, it consists of just 353 million operation. In the naive case, we have how many? 854 million. So this is a big, reduction in terms of number of operation, right? Okay, so any questions so far on the description of the GoogleNet and AlexNet? Nguyễn Hoàng Anh have question. Where can we use filter for by 3, actually you can. But I don't see any, practical benefit from using that filter size. Another question from Trần Quốc Khánh. Why CNN is better than fully connected RNN in image classification? Okay, so for this question, I understand that you want to compare CNN to fully connected neural network, right? So by CNN neural network, you have the possibility to have a very big neural network, right? But the number of parameters is very less in comparison to the fully connected neural network, right? Because in the CNN, the number you see the way that we have the CNN neuron that slide from left to right and from top to bottom, right? So you reduce the number of parameter. And you see that for the image, actually the data in the image have the structure information, and the the CNN was designed to really work and capture that structure information of the image. Why Google Net don't use fully connected but still give better result? So for this question, I am thinking that the fully connected layer is not necessary, but of course you can implement the fully connected layer after the Google Net. But I mean the implementation, so that there's no need to add that layer. Any questions so far? I mean the performance of the Google Net, it was from the fact that they have very special special way to design the network. They implement the inception block that can how to say make the network to be very deep, right? But the number of parameters to learn is very less in compared to other way of architecting the network. So the performance is from the inception model, is not from the from the use of fully connected layer or not. Why don't need to use fully connected? I just told you that you can, right? But according to the experimentation, there's no need for using that fully connected layer. Without that, the performance still good. You don't use a fully connected, but you still use a softmax, right? To make the output to be the distribution of different classes. Any other question? Hello. Okay, then I think that we can continue with ResNet. Okay. So ResNet was proposed in the paper did residual learning for image recognition in 2015. The network is very deep, up to 152 layers. The deeper the network, the harder it is to train. This is the observation from training the network, right? Because for the deeper network, we will highly affect the, we will highly receive the gradient explosion or vanishing problem, right? And the RedNet will propose, the RedNet propose a residual learning method that allow to efficiently train network much deeper than the one that came before. So now we will see how the RedNet can doing with the training of very deep network. Okay, so about the performance of RedNet architecture, it was a champion of the IL SVRC 15, and it reduced the classification error by to be 3.57%, and it is better than the human, right? And this architecture was used for almost all the contests, and it got the state-of-the-art performance at that time. Okay, so here's the architecture of RedNet. You have the input, and then the convolution, and then the pruning, and then you have that spatial block that was repeated, and in that spatial block you have the convolution layer, right? And then you have spatial, shortcut from the input to the output, right? And also you have that shortcut. Okay. So here's just a discussion about the performance of the network when we increase the size, increase the depth of the network. Normally, for example, here is a test with the network of 56 layers, and from this side of depth, people observe that, even when we increase the number of iteration, the training error of that very deep network is worse than the training error of the smaller network, and this error exists even for the test case. The smaller network is somehow perform better than the deeper network. Okay, and it is said due to the degenerative phenomena of neural network, due to the either gradient explosion or vanishing gradient. Okay. Okay, so about the RedNet. Okay, we have the idea that the very deep network are harder to optimize, right? Because from this experiment, we see that, okay, if we have no special way to design the network, then a very deep network will perform, worse than the the shallow network, right? So the solution of RedNet is to be this way. Let the network layer to learn the residual representation. The residual means the difference between the output and input, instead of directly learning the output as before. right? So actually in this is the normal case, you have the input and then this is a neuron block and then the output, right? So in this case, you want the model to learn the, the S function here, the output of the neuron block, right? And in the RedNet case, okay, you have the shortcut from the input to the output, right? And in this case, you somehow force the model to learn the differences between the output and the input, right? And to be easy to understand, you might think that okay, you have the shortcut that gives the senior a chance to go directly from the input to the output, right? And in the other case, every senior have to go through different layer, and in that way, you may lose the information due to the vanishing gradient or gradient exploitation. And in the other case, in the RedNet, you have the shortcut so that the information can bypass, that block and go directly to the output, right? Okay, so that was the idea about the RedNet. Okay, so for the RedNet, you have a stack of residual blocks. So an residual block have two 3x3 convolution layer, and you periodically double the number of convolution and decrease the resolution by convex stripe 2. And you have a sublayer convolution at the top of the network, and then you have no fully connected layer at the end, only the this layer to do the softmax classification. So you see the feature from the lower layer can go through the shortcut, and it can directly go to the upper layer, right? Okay, so for the network presented in the paper, they propose the experiment with the network dip of 34, 50, 100, and 152. And for the net with more than 80 layer, they use a bottleneck layer 1x1 convolution, similar to the Google Net, right, to increase the efficiency. Okay, so here is the evaluation of different model that show you some recent state-of-the-art performance over the ImageNet classification. Okay, so in the x-axis you see the number of parameter, and then in the y-axis you see the accuracy. And the RedNet we have somewhere here. This is RedNet 152. Okay, top one accuracy is okay around 78%. Top one. Okay. You have more recent net, such as the EfficientNet, AMO AirBarNet, and SNNet, right? So there are recent work that implement special mechanism to do the network hyperparameter search, right? And then you see that with EfficientNet V7, you will have the highest score with the less number of parameter. Okay, another comparison with different neural network model. Okay, so any other question? Do I have any question? I think that you can talk, right? It could be better to talk than chatting over the message box. Any question?
Teacher.
Yes.
Can you go back to the slide 40?
40.
Yeah.
Yes.
The VGCnet, the slide, I think in the slide VGCnet, no, the previous slide. Can you explain again about the rest parameter 3 times 3 square and c square?
Okay, so assume that you have the input is let's say the size 1, 1, 2, 112 and 112. Okay, and now you apply the 7x7 filter. So what is the size of the output? If we have the stride equal to 1, so what is the size of the output? It would be 1, 0, 1, 0, 6, right? 1, 0, 6. Is this correct?
Yes.
Okay. And now in the case we have 3 by 3 convolution, right? 3 by 3. Okay, so after the first 3 by 3, 3 by 3, which is the output side? This is 1, 1, 0, right? Is it correct? And then the second 3 by 3, it is 1, 0, 8. And then another convolution layer, the size of the output is 1, 0, 6. Okay, so you see that, I mean, if you apply the 7 by 7 convolution layer with the 3 by 3 convolution layer, you got the same output size, right? Is that correct?
Yes.
So in that case, it is said that they have the same output representation capacity, right?
Yeah.
But the thing is, I mean, you have less parameter and more non-linear layer. So that was the idea about the advantages of using small filter. Is this okay?
Yes, I think it's good.
Do I have any question? Okay, so I might say to you some live to practice a little bit. Okay, so I said to you, lab consider 3 notebook. So I think that you first look at the convolution network notebook, and then the convolution network raw notebook, and then the RedNet notebook to see how is the implementation of the network.
I will open the raw first or the non-raw first?
The non-raw first.
Okay.
Okay, so you have some time to take a look into the notebook and understand what was the idea, right, of the notebook, and try to do some exercise. I leave it alone for, let's say, 30 minutes, and then I will be back at 15 to 3. Is this okay? Is this okay like this? Okay, so see you at 15 to 3. Okay.